This is a visit teletraining on how to use GOES-R data to identify blowing snow. I'm Scott Lindstrom from CIMSS. This is work that was originally done by Carl Jones, who's a meteorologist in Grand Forks. I was also helped by Dan Bykos at CIRA. Satellites have viewed blowing snow in the past before GOES-R. This is VIIRS imagery, visible imagery, from 2013. VIIRS also includes a 1.61 micrometer channel, similar to the Snow Ice Band 5 channel on GOES-R. And that data was used for this picture. It's colored so that red regions are ice, whiter regions are liquid water clouds, but you also see blowing snow in this image. Blowing snow will often show this linear appearance in satellite imagery. So you have these horizontal roll vortices that stretch downwind. Notice if there are stations that are reporting blowing snow that are close to these horizontal roll vortices that you see in the satellite imagery. GOES-R includes channels in the visible and then the near infrared in which snow is highly reflective. The example shown here has high reflectivity in the visible image at 0.64. This high reflectivity also occurs in the veggie band, band 3 at 0.86 micrometers. Compare this high reflectivity to the very low reflectivity you see over snow and ice in 1.6 micrometers. Snow that looks very bright in the visible or in the veggie band will look darker in the 1.6 micrometer snow ice band. It's a way to discriminate between clouds and snow. The day Snow Fog RGB is an AWIPS. This RGB includes in the red the veggie band 0.87 micrometers. This has good contrast between water and land surface characteristics, and it detects clouds as well. Clouds over snow in the 0.87 micrometer are difficult to detect though because everything is bright white. The green in this RGB is the 1.61 micrometer snow ice band, and this is good for distinguishing between clouds made up of water droplets and underlying snow. The blue in this RGB is the day fog brightness temperature difference, 3.9 minus 10.3. 3.9 micrometer is usually warmer during the daytime because of reflected solar radiation, and the amount of radiation reflected is a function of particle size. Very small particles reflect more incoming solar radiation, so the day fog brightness temperature difference will be larger. The bounds used for all three RGB components are down at the bottom. All three also have an AWIPS gamma of 1.7. That's gamma in the classic sense, which, as you might remember, is 1 over gamma in the composite options. This gamma value will emphasize the low end of the range. Why does this detect blowing snow? Snow reflects a lot of 0.86 micrometer radiation, so there will be plenty of red in the RGB. Snow is pretty dark in the 1.6 though, so there won't be very much green, and the day fog values are also small over snow. Blowing snow increases the reflectance in the green and in the blue, so there's a color difference in the RGB between snow and between blowing snow, and there's a textural difference as well. Snow that is blowing has the linear features in it. Why is that important? You can use the RGB to understand where the blowing snow is occurring, and you can use that information to change where a warning might be. At 15Z, a blizzard warning is ongoing in counties surrounding the Red River of the North, the border between Minnesota and North Dakota. The blizzard warning was trimmed at 1858Z based on information from the day Snow Fog RGB, which shows blowing snow mostly over Minnesota. Use other datasets to confirm what the satellite is showing you. For example, here we have 3 different webcams, here, here, and here, and they confirm what you might assume is happening at the surface based on the satellite imagery. Also keep in mind antecedent conditions. How likely is the snow on the ground to blow around? Is there any crust on top of it? Is it fresh? The satellite information allows you to trim your warning as needed. This shows the composite options for the day Snow Fog RGB and AWIPS. The red component is the veggie band. Clouds and snow are highly reflective. The green component is the snow ice band. It distinguishes between ice, which is not reflective, and cloud water droplets, which are highly reflective. It also discriminates between snow on the ground, which is not very reflective, and blowing snow, which is a bit more reflective. The blue component is the day fog brightness temperature difference. This highlights features such as small cloud droplets and small ice crystals that are more reflective for 3.9 micrometer radiation than for 10.3 micrometer radiation. All three RGB components have a gamma of 0.59. How does that affect the display? Gamma less than 1 means that the component of the RGB is weighted so that small changes in the low end of the values will be visualized, whereas small changes in the high end values are not visualized quite so much. This also shows the ranges that are used in the RGB, and they differ from the default ranges if you load the individual components into AWIPS. So typically when you load a 1.61 micrometer image, which is used for the green, the range of values is greater than 0 to 70. It's usually something like 0 to 130. Here's the RGB in the bottom right with the default components in the other three squares of this 4-panel. And I've loaded them with the default values. So the 0.87, the red, is loaded with default values from 0 to 130, so is the green, and the day snow is loaded with values from -5 to +60. If you're going to load up the components of the RGB in a procedure as a 4-panel, you might as well load up the imagery as it's used in RGBs. This shows an animation of the RGB in the bottom right. One thing you'll note right away: the RGB doesn't give you surface information until the clouds clear. You can see linear features where the blowing snow is occurring. In each of the three components, the veggie band, the snow ice band, and the day cloud fog difference, that really helps you identify where the blowing snow is. You could make a guess based on the still image where the blowing snow is, because you'll notice that the blowing snow has a distinct or unique color in the RGB. Use the RGB to inform you of where the blowing snow is occurring. Looks like it's starting over this lake in Manitoba, and then the blowing snow moves downstream. This is 5-minute imagery. If you wanted to see things even more clearly, you could call a mesosector and look at 1-minute imagery. Here's a day snow fog RGB that's just a still image. Can you pick out where the blowing snow is based on the color of the RGB and also maybe some linear structures that you see? There was blowing snow on this day in 2019 over much of north-central Iowa. Notice the linear features in the RGB, the slight difference in the RGB shade compared to the underlying snow. Those two things tell you that blowing snow is occurring. In the previous image, the color change was pretty subtle. Don't be afraid to call up the composite option in the RGB and tweak the colors to bring out the contrast and the details. Look for those color details and also the linear features aligned with the mean wind. That will tell you where the blowing snow is occurring. Here are animations from that day. Use the animations to determine when the blowing snow starts. The day snow fog RGB is in the upper left. The veggie band is in the upper right. The snow ice band is in the lower left. And the day snow fog is in the lower right. At the end of this animation, we do see the beginnings of linear features being shown in the day snow fog RGB. A little bit later in the day, we see in the day snow fog a pretty clear indication that blowing snow is being detected by the satellite. We have the different color in the RGB from the underlying snow to the south and to the north. This region in central Iowa is where you would expect to see the greatest visibility restrictions due to blowing snow. Now let me animate this. On this day, it looks to me like clouds are starting to form as well above the blowing snow. The blowing snow signal, which is initially this orange-yellow color, is being overtaken by some whiter colors, which are more typical of clouds moving in. at the end of the day you see a much stronger signal of clouds. Now of course there might still be blowing snow down at the surface. It's difficult to tell because the clouds are getting in the way. Multispectral GOES-R data allows you to view blowing snow in clear regions, make a procedure to load up in one of the panels the RGB, and in the other three panels the three components, the red, green, and blue, scaled appropriately. You can tweak the RGB components during low sun angle times. Typically what you need to do is reduce the upper bound of the reflective bands. And as I've noted, this doesn't work with cloudy skies. I have not yet tried this with thin cirrus. I'm not exactly sure what blowing snow would look like underneath cirrus. That's something you can look at in the coming cold season. That's all I have today with this short training. Thanks for listening.